In the previous video, we got the derivative of the optimal value function with respect to the constraint constant. The expression for that we got as lambda times g sub x times dx star by dc plus g sub y times dy star by dc. Now let's try and get a sense of what this expression here is. We've already got our Lagrangian multiplier into the picture, because ultimately we have to get an interpretation of the Lagrangian multiplier, so that's already in place. Let's see what this expression boils down to. Okay, now note here that our constraint was g of x comma y equal to c. Okay, so if I evaluate this constraint at the optimum, what am I going to get? G of x star of c comma y star of c is equal to c. And now if I differentiate both sides of this equation with respect to c, let's see what I get. I'm going to get g sub x evaluated at x star comma y star times dx star by dc plus g sub y times dy star by dc is equal to 1, because the derivative of c with respect to c is 1. And this, you can see here, the expression on the left hand side here is exactly what we have here. So this then gives us the result. Once we put this expression in brackets equal to 1, I get the derivative of the optimal value function with respect to the constraint constant as my Lagrangian multiplier. That is the interpretation of the Lagrangian multiplier. It, it tells us the rate at which the optimal value of the objective function, the value of the objective function at the optimum, changes whenever the constraint constant changes. Now, for example, in our previous example that we just worked on, the utility maximization problem, our constraint constant was nothing but our money income, and the optimal value function was being interpreted in terms of utility. So in that utility maximization problem, we had du star, the derivative of the optimal value function, which u star here was a function of money income, and the derivative of u star with respect to money income would then not be nothing but the Lagrangian multiplier. Now actually we can give a nice economic interpretation to this expression here, because if you notice, the derivative of this optimal value function, the utility function at the optimum with respect to income, is nothing but the marginal utility of money. This expression reflects nothing but the marginal utility of money, and therefore in the utility maximization problem, the interpretation that we can give to the Lagrangian multiplier is nothing but the marginal utility of money. In general, what we can do is we can think of this constraint constant c as representing the stock of some resource. And we could think of our objective function f of x comma y in terms of profit or utility, and therefore the interpretation, the economic interpretation that we give to lambda is then a parameter that reflects an increase in profit or utility as a result of changing the stock of the resource that we have. So for example, if I have DC more units of the stock, what will be the increase in profit? Or in terms of the utility maximization problem, if I have DM more units of money income, then what will be the increase in utility at the optimum, right? So this is the interpretation of the Lagrangian multiplier. Economists very often refer to the Lagrangian multiplier as a parameter that reflects the shadow price of a resource. So lambda can also be interpreted as something that reflects a shadow price of a resource. Shadow price is something that reflects, it's a price that reflects the true scarcity value of a resource, the true value of a resource. So the market price, for example, may not reflect the true value, the true scarcity value of a resource, but shadow price is something which is supposed to reflect that. Okay, so that's all that I have for the teaching part today. What I would like you to do next is practice a few problems. So one problem could be this. Let's say you have to max and minimize 3 times xy. This is your question for practice. And so you have to maximize and minimize 3 times xy subject to the constraint x square plus y square equal to 8. What I would like you to do is try and work on this problem first through a graph and try and get a sense of what kind of a where you'll get your optimum on the graph, and then do this problem with the math. So just to give you a hint, in this problem you're going to get 4 stationary points. You'll have 4 stationary points to work with. Okay, so this is what you'll do for your exercise question. Another question that you could do, I'll since this video is becoming a little long, let me just assign it on the WhatsApp group.